Okay, I think we're live. Welcome if you've joined. Let me know you can hear me. I hope we're all keeping well. Lots going on, I'm sure, in terms of keeping on top of your schoolwork and stuff. But hopefully these sessions will be really useful for you. Welcome. I can see that there's a few people watching. So hi, welcome, and feel free to comment in the chat. Hi, excellent, cool. So what we're going to look at today is we're going to look at a bit of composite and inverse functions. So this is really very much an A-level topic, part of the pure maths. And I think one of my colleagues has just dropped in a link for the slides that we're going to run through if you did want to run through this at the same time. So we're going to look at functions. Functions is a massive chapter, often covered in year 13, but actually kind of the basics are started in year 12. And it just builds and builds. And I kind of think on the surface, it looks like a fairly straightforward topic. We've seen the notation before, but actually traditionally in exams, it's a topic that a lot of A-level students mess up, or there's kind of parts of the question that they sort of fall down on. So that's what we're going to be looking at today. It'll be great if you can interact alongside and, let me know if there's any issues or that you're understanding it as well. So that would be great. I'm going to share my screen now with you. So do let me know that you can see this. I'm about to share the presentation I've got ready for this. So here we go. Hopefully you can all see that. I'm going to make that full screen for you now. Right, excellent. So we are going to look at composite and inverse functions. And this may be a topic you're familiar with. Certainly the notation, even if you've kind of just got your GCSE knowledge, you will have seen composite functions. You will have seen the notation for it before. So hopefully this will be really useful for you. As I said, a really important A-level topic and something that filters into everything. It kind of goes into calculus. It affects a lot of the pure maths. So really important topic that we're going to run through today. I'm just going to sort my screen out so that I'm ready to start working through these questions. And we're going to look at basically exam style questions today. So let's have a little look. So first thing to point out, towards the end, you're probably aware that we do this. There'll be a coupon code for everyone, which will be a discount for Snap Revise and the platform that we have. So if you like these lessons and you kind of want more and you want to be able to attend the drop-ins and stuff, I'll speak a little bit about that towards the end. But what we're going to do to start with is we're going to crack on, look at functions and look at how composite functions and inverse functions come up in the exams at A-level. So this will be a really important and useful topic, hopefully, but feel free to contribute, share answers and questions in the chat. Excellent. So here we go. So this first question, this is a very typical question for functions. This kind of scenario, the big idea that's kind of going on in the background for functions is this idea of domain and range. So domain being the allowable X values or inputs to the function, and the range being kind of the Y values. So this is both A-level and AS kind of targeted. It's examined more heavily in year 13 in the full A-level. We go into a lot more detail, and the stuff we're going to cover today will largely be targeted at that, but domain and range and this notation and everything could come up throughout. So this will be useful for both really, whether you're year 12 or 13. It's a good insight into how far this content will go. Okay, so here we've got two different functions expressed as mappings. So the function f maps x onto 1 minus 2x cubed, and the function g maps x onto 3 over x minus 4. And these bits here are what we would refer to as the domain. So this is telling us our allowable values for x. And you'll probably notice from, if you've looked at papers or past papers, that this is basically given in the question sometimes, and a lot of the time we kind of glance over it, but it is important. So you may have seen this written in AS kind of stuff before. You might have seen a domain tagged on and thought, I don't know what to do with that. Maybe I need to, sub those values in. This is given, domain and range is covered in year 12, but we extend on those ideas in year 13. So as I said, this is appropriate before. That notation may well be new to you. Good, yeah. So you might have been used to defining your function as f of x equals 1 minus 2x cubed. That's fine. That is just saying the function is equal to that. That's absolutely fine, yeah, and I'm glad we've picked up on that point. This is just, it essentially means the same thing, but it would kind of be read as the function f maps x onto that. So this is still the input and this is the output. So it's kind of the same scenario, they've just used the mapping notation. So that's absolutely fine. If that's new to you, we still deal with it as we would with functions. Okay, excellent. So to find the inverse of the function f, and the notation for it is f minus 1, this might be something you've seen before, but in order to do the inverse, we can basically use the little trick of call it y equals and then swap x and y around. So for example, if I say, right, y is equal to 1 minus 2x cubed, in order to do the inverse, and that's a good point, this is not the derivative. So the notation looks very similar to f dash of x. That is not what we're doing. We're doing f minus 1. That's the inverse of x. Good. Bit like how arc sine minus 1 is the inverse of sine. This is just general notation for the inverse of f. Very good and well pointed out. So this is not differentiation, no. So here we go. In order to do the inverse, we basically change the subject. We make x the subject. So what we could do is add 2x cubed to both sides and minus y, and we'd get 2x cubed is equal to 1 minus y. And then what I'd do is divide through by 2. So 1 minus y over 2. And then I'd get the cube root of both sides. So you could write it like this. Or like that. Now the final answer, just to be really clear, is we've only used y to help us do the little rearrangey trick. Functions are defined in terms of x. So you've only used y as a sort of thing to hold the place and allow us to rearrange. You should state your inverse in terms of x. So as a kind of mapping, you could write it like this. And it would go to 1 minus that value over 2 cube rooted. And hopefully we're clear that if you wrote the cube root sign or you wrote to the power of a third, they're the same thing. So that would be an equivalent answer. So basically what we had to do here was rearrange it and make the input the subject, and then just remember to use x in your final answer. So using y allows us to basically just rearrange and change the subject. But what we've done is we've found the function that undoes the original one, which was f. Okay, so 1 minus 2x cubed, to undo that, you do 1 minus the value divided by 2 and then cube rooted. So that is the inverse function. It may have been something you've seen before, or this might be quite new to you, but you do need to know how to find these inverses by changing the subject. The actual skill is very much a recap from GCSE of rearranging and changing the subject, but it is worth doing very carefully and making sure we get bang on. Right, let's carry on. So here, show that the composite function g of f, yeah, absolutely. I've just seen the comments come through. Yeah, the notation of the mapping might be different, but the process is something we recognize. So that's brilliant. So the composite function g of f is given as this, and we want to show that. So this is kind of bringing to light how A-level is very much all method based. They've given you the answer. They want to show how you get there. Okay. Now g of f of x, and you might recognize this at GCSE. They might have written it like this, or they might have even really gone heavily used the brackets as well. But g of f of x, you work from the inside out. So it means you put x into the f function first, and whatever comes out, you sub that into the g function. Okay. So this is for all boards. This is really crucial for all the A-level exam boards. So it is worth paying attention to this method for whether you're AQA, Edexcel, OCR, and so on. Functions is crucial to all of them. So yes, absolutely. Lovely. So let's have a little look. Right, so what we can do is the output of f of x would be 1 minus 2x cubed. So whatever I put in comes out as 1 minus that thing times 2 and cubed. So what I can do is basically do g of f of x is essentially equal to g of whatever comes out of f of x. And what comes out of f of x? 1 minus 2x cubed. And I know this sort of thing trips people up at GCSE even. Okay, so what we have to do is put that basically in as the new x. That's the new input into the g function. Okay, so what we get there is we get what the g function does. It does 3 over the input minus 4. So what we're going to get is 3 over all of that minus 4. So now we've kind of got it all in terms of x, but we're trying to show that it equals this. So we need to do a little bit more manipulation here. And the way we can deal with the 4 as a fraction, if we think of fractions and common denominators and stuff, hopefully we're happy that 3 over this, 1 minus 2x cubed, minus, well, 4 would be like 4 lots of that thing over itself to kind of give us the common denominator so we can combine it as a single fraction. Okay, and then that can be written as 3 minus 4 lots of 1 minus 2x cubed, oops, all over that common denominator. And then we get, hopefully, so 3 minus 4 is the minus 1, and minus 4 times minus 2x cubed is 8x cubed. So we get 8x cubed minus 1 over the thing. Okay, so just checking over the questions there to check we're all following okay. No, so this is not specific to an x value, but a very good question. Sometimes it will say g of f of 2 or f of 2 or f of 5, and you have to sub that specific input in as x. So what we're doing is we're doing the whole question in general terms. So the input is x, and we leave everything in terms of x through the whole process. So yeah, absolutely. So some of this is very much an overlap with GCSE, but it will build, and we need to be absolutely clear on this method. So basically what I've done is I've taken x, just in general terms, and what would come out of this function, 1 minus 2x cubed. Obviously, if they said f of 5, you'd put 5 in and get a number out, but we're putting x in. Then that bit comes out and becomes the new input into the g function, because we've got to now sub the output of that into the g function. And that is 3 over the input minus 4. So 3 over the 1 minus 2x cubed minus 4. So we've kind of done it. We have put x into f, then whatever came out, we've put it into g. But that's not how the answer was what they wanted. They didn't want it expressed like that. They wanted it as a single fraction. So all this end bit was basically combining it as a single fraction using common denominators to give the desired form that they wanted. So 4 marks there. So basically a couple of marks for subbing it in, and then a method mark for doing the tidying up, and then a final answer mark. Okay, cool. So we'll move on. Now what we've got here, the function here is defined by x is basically being mapped to ln, the natural log of 4 minus 2x. And what we can see, or we could start to see the overlap with the year 12 content, is it's also this sense of transformations, understanding graphs, being able to sketch graphs. That's all really important as well. So some of these questions will quite quickly get a bit more involved and get trickier and rely on other knowledge. But if we have a really firm understanding of what are the inputs, what are the outputs, we can quite carefully analyze what's going on. So here it says show that the inverse function of f is defined by this. So again, it's a show that. Now it also says write down the domain of the inverse. Okay, they've given us the domain of the original function, and you may well be aware that for inverse functions, the domain and range switch, because basically what were the inputs are now the outputs, and what were the allowable outputs are now the inputs, because they're inversing each other. So what we're going to do, we'll start by just doing the inverse, trying to show that it equals that, and then we'll look at its domain. Okay, and then it also goes on to ask for the range. And notice that this is a little one marker, because I'll explain where that comes from. Yeah, so some of this stuff might be new to you, but it's probably worth paying attention to the general setup, even if some of the content is new. So you might not have done logarithms before, you might not have done natural log of x, but I'll show you how the process works. And certainly, you know, you could watch this back, or you could kind of look at some of the later examples we're going to talk about as well, and piece these bits together, but I'll run through it anyway. So what we've got, the same method as before for part A, and that's not an A, there we go, is let's call it y equals ln of 4 minus 2x. Now, for those that have seen the natural log, they'll realize that that was the inverse function of e to the power. Okay, this might be very new to you, no problem if so, but I'm just going to go through the method in the same style that we would have for the previous example. So in order to undo ln and try and make x the subject, we raise both sides to the power of e. So this would be e to the y equals 4 minus 2x. And then what we're going to do is we're going to make x the subject. So if I add 2x to both sides and I minus e to the y from both sides, I get 2x equals 4 minus e to the y. And then I divide 3 by 2, and I get x equals 4 minus e to the y over, whoops, 2. Sorry, crammed that right in the bottom of the page. So what I get there is that will tidy up 4 over 2 minus e to the y over 2, which equals 2 minus y over 2. And remember, we've got to put it back in terms of x, because we just used the y thing as a mechanism to help rearrange. So that means that f minus 1, the inverse function of x, maps x to 2 minus a half e to the x. Okay, yes, absolutely. So e and natural log of x, so ln and e are inverse functions of each other. So if you haven't seen those before, understandably, that step will be quite strange and be kind of confusing. But it would be like how sine and sine inverse, sine arc sine are the inverse functions. X squared and square root of x are inverse functions. So when you've done that logarithms and exponentials chapter, you'll learn that notation, you'll learn about those numbers, and you'll learn about those functions. But after that stage, it's very much the same as before. Make x the subject, and then rewrite it in the inverse way. So if this bit is new to you, then absolutely that would have meant you struggled to get started there. But from then on, it's the same as before. You just get x isolated on its own, and then you put it back into the inverse function notation. Okay, cool. Yeah, so it's a function that it's an exponential function e. So that deals with something 2.7 blah 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 to the power of x. And it has an exponential shape, and then the inverse is a logarithm. So, but the method is the same. So that was another show that, but it did say write down the domain of the inverse. Now, the domain of the inverse is actually the range of the original. Okay, and the range of the original is actually any real number. So this we can write as x belongs to the reals. This is just notation you need to know. So basically x, the domain, x can be anything. We could put any value for x in here and we'd get a number out. It won't cause a problem. The range, however, is the y values you can get out of this. And actually, you can't get any y value out, because if you've got 2 minus a half of something to the power of x, you've kind of got an asymptote, you've kind of got a bound. Excellent, and some really good suggestions coming in. There's actually a little shortcut to this question, and this is why I've pointed out it's 1 mark. They love to do this because this is about spotting something. The range of the inverse is actually the domain of the original function. So they've kind of given us it in the question, and that's why it's only 1 mark. So you don't have to draw the graph or anything. You just need to recognize the domain and range swap. So what we get as the range is that you could call it y, but I would be really careful when you use the notation in the question, f minus 1 of x, or the output of that function, is less than 2. So it's like y is less than 2, or we'll call it f minus 1 of x is less than 2. So basically the point I've kind of got to in that is that the domain and range switch for inverse functions. And hopefully when we look at the graphs a bit more, we can kind of explore why that happens. But basically the inputs become the outputs become the inputs. So the values that they can take, those sets of values swap. Okay, so if I know what the original x values were, x had to be less than 2, then that's what the outputs can be for its inverse. Okay, and as before, guys, this something I always encourage. If you're struggling with graph transformations, or you think, I don't really know if I could even sketch that graph or how I'd do this, software like online software, there's loads of free graphing software, Desmos, GeoGebra, and so on. You can type the functions in and see what it looks like, and it kind of brings it to life a bit more. But we're actually going to carry on with this question because we'll have a little think about how this graph looks and why that is an appropriate answer. So let's have a little look. So here is this same question, part C, is asking us, in the space provided, sketch the graph of the inverse. So state the coordinates of points of intersection with the axes. Let's just remind ourselves what was the inverse. It was 2 minus a half e to the x. I'm going to write it like this. Okay, now what this looks like is it's got an asymptote at 2. Okay, so this is the line y equals 2, and it's going to have a shape that looks like this. Okay, so this is y equals 2 minus a half e to the x. Now this does come back to graph transformations as well. Okay, because if we think about it, remember, if you have x squared and it's kind of the happy way up, and you do minus x squared, it reflects it in the x-axis. So when you have a minus in front of the exponential function, it reflects what would have been the positive way up downwards. Okay, so this function is going to kind of get more and more negative. Now, what goes on here is that the asymptote is 2, because we've done a translation rather, up by 2 from 0. And then the other key thing we need to do, it does say it in the question here, is the points of intersection with the x and y axis. Okay, that's actually a very standard thing at A level. When they ask you to sketch, they're looking for, have you got the shape right? Like, do you understand what it looks like? Have you got any asymptotes in the right place? Have you got any turning points, if there are any, in the right place? And have you got the intersections with the axes? Because obviously it is a sketch, you're not expected it to be like a computer, but it needs to look right, and it needs to have those key features done correctly. Okay, so what we do here is we put the asymptote in, because hopefully our range already told us that. But any ideas how we can find these points? Okay, and don't overcomplicate it, that you can do this for any function. There's a very simple part of the coordinate we can use. Excellent, some people have already got answers to this, but this is doable even if you've never done this type of graph before. Absolutely, you're basically trying to find coordinates where here y is 0 and here x is 0. So sub x is 0 in and sub y is 0 in and solve. So for the y-intercept, you know that that happens when you sub x in as 0. So the y-intercept is going to be, for this graph, is going to be 2 minus a half e to the 0. Now remember, anything to the 0 is 1. So it's 2 minus a half times 1, which is 1.5, 3 over 2. So that is 3 over 2, or you could write 1.5. So what we've done is we've put x in as 0 to get the y-intercept, as we would normally. And in a very similar way, yeah, excellent suggestions coming in, we put y in as 0 and try and solve it. So 0 equals 2 minus a half e to the x. And again, if you haven't done the logarithms and exponentials chapter, this would be quite tricky for you. But what we'll do, we'll rearrange that and we'll say a half e to the x equals 2. So e to the x equals 4. And then you take the natural log of both sides, so x equals ln of 4. And that's the exact answer. Okay. Sorry, it's all kind of crammed there, guys, but hopefully that's clear. So ln of 4, 0 would be a point on that curve as well. Absolutely. Now, in pure maths, in the pure maths content, generally we're looking for exact answers. So leaving it as a fraction, leaving it in terms of pi, leaving it as a surd, leaving it in terms of ln or e, unless otherwise stated, unless they said giving it to a free SF, I would give it exactly. So that is spot on, just leaving it like that. Okay. No, so there is no real way you'd want to simplify that. That is spot on. You don't need to put it as a decimal because that's kind of making it less exact. And ln of 4 is spot on. It's bang on. It's an exact value, so you don't need to really change it at all. You don't need to like write using different bases or powers. That is absolutely fine like that. So good, excellent questions there, guys, and good comments as well. It's good to kind of get a sense of what people have done as well at this point in the year, because obviously with everything that's going on, and you know, we're all from different schools, different backgrounds, with different backgrounds in mathematics, we're thinking, well, I haven't ever seen that before. And some people might think, you know, I've done a fair bit of this, but it's relevant to all of us. So really important that we check and ask the questions as we go. Right, lovely. Let's keep going then. So this one here, again, the skill is very much a high-end GCSE skill that people mess up, but it's knowing that this is how we do an inverse function for something like that. Okay, so what we do here is the same process. It's just that the rearranging is a bit tougher. Okay, so what we do, let's use the y trick thing again. So write y in terms of x to allow us to rearrange it. And then what we do is from there, we basically go, okay, I want to make x the subject. Okay, and this might be something you want to work ahead and give a quick go now. I'm going to run through it. So the first thing I would do here is kind of times up by that denominator, and I'd get y times x minus 5 is equal to 3 minus 2x. I'd expand it out and I'd get xy or yx minus 5y equals 3 minus 2x. And this is the point that I've noticed a lot of students get kind of stuck at this stage, because there's all these different things mixed around and we forget what we're even doing here. And excellent for those answers that are coming in. They're all looking sensible and good, but we're going to go through very carefully from here. Now, remind yourself at this stage, what are we trying to do? We're trying to make x the subject. We're trying to get all the x's on their own on one side. So this is going to need a bit of manipulation. We're going to need to rejig it. So I'm going to get all the x's on one side, everything else on the other. So I'm going to get xy. I'm going to add the 2x across and add the 5y across. And I get this. Now the key bit is to get x on its own is basically we factorize. So I've got xy plus 2x. And I want x, so I can factorize it out as a common factor. So x brackets y plus 2 is equal to 3 plus 5y. And now I can divide through by y plus 2. So x is equal to 3 plus 5y over y plus 2. And remember, that's not how we leave our answer. We put it in terms of x. So the inverse function of x is equal to 3 plus 5x. And well done if you did get this already. That's brilliant. X plus 2. Or you might have wanted to give that as a mapping. That is fine as well. Write it like that. Okay. So again, thanks very much. Lovely comments. The thing to point out here is you have done this skill at GCSE. You have done this. This is probably, when I've gone through this with year 11s, this has been one of those harder topics towards the end that is just very algebra heavy, and we kind of halfway through like forget what we're doing. We kind of think, oh, I'm just moving stuff around and manipulating algebra here, and I've even forgot why I'm doing it. But actually, it is to find an inverse function. It is the same process as all of the other questions, but it's just a nastier looking scenario from the off. But we've now got the inverse function, all in terms of x, all nice and tidy on one side. So that's great. And 3 marks there. So there was nothing sort of mind-blowing, but it was very easy to go wrong. Okay, so just be very careful with these questions. No, I don't think, that's a really good point there. I don't think, if you wrote it like this instead of like this, I think you'd probably be fine. But what might be worth doing for your exam boards, whenever you have questions like that, which are really worthwhile to check, look at some mark schemes for your board and see how picky they're being. Generally, and sometimes even the examiner's reports are really useful. I think that would be very harsh to mark you down on that, especially when it's quite a low amount of marks for the question anyway. So probably not, that's probably fine. But just try and be consistent with their notation, because they can be picky on that. For example, if don't use y, use f of inverse, that's where you're likely to lose marks. So if they've used function notation, a bit like in calculus when you do differentiation, if they use y, you use dy dx. If they use f of x, you use f dash of x. So you just keep it consistent with the question, and that's the safest way to go. Okay, excellent. Right, let's keep going, because we're doing really well here. Now, this is an interesting one, because this function, this is part of the question we've just done, except this function here is a completely different function. So the function here, this is the function they're calling g. This is g of x that's shown here. So that is not what that f function looks like. This is another function as well. And the question says the function g has domain from -1 to 8 inclusive. So it goes from -1 up to 8 and is linear from -1, -9 up to 2, 0. And then from here, 2, 0 up to 8, 4. And this type of function is actually what we'd call a piecewise function. And you start to see this thing even in statistics, because what happens is you've got like 2 separate domains, and then there's different outputs based on what's going on at that stage. So this is a very different setup function, but they've given you the graph for it. So the first part of the question, you were dealing with this, you found its inverse and so on. The second part of the question, they've given you this random function, g of x, but they've given you the graph of it, so you can kind of see what's happening with it. Okay, and then it says write down the range of g. Any suggestions here? Remember what range refers to. So you've got domain referring to the inputs or the x values, and then you've got the range referring to the outputs. So they've given you the domain, they've given you the domain of g, they've given you the graph of g. Excellent, right? Some suggestions coming in. What's the range of g? It is between, I've just lost track of what I was going to say there. Yeah, absolutely, between -9 and 4. Cool. So -9, and we can write, we'll write g, not y, because we're talking about this function we're calling g, and less than or equal to 4. Now, something just to perhaps highlight is the strictness of the inequality. You basically go with the strictness of the bounds over here. Okay, so because originally it was between -1 and 8 inclusive of -1 and 8, then this goes from -9, 4 inclusive of them as well. Okay, so what we've got is essentially what we've done here is the domain. Let's use a different highlighter here. The domain is talking about what x can be between. X can go into this function anywhere between -1 and 8. And the range that we're dealing with here, anything can come out of this function between -9 and 4. So range, you're looking at y values, domain, you're looking at x values. Okay, and hopefully that's kind of clear. But this is something we constantly reinforce throughout year 13. So domain relates to inputs and x values, which we can see for the g function here goes from -1 to 8, because they tell us that, and we've got the graph. And directly from the graph, we can see the numbers that can come out as a y value, as the y part of the coordinate, is anything between -9 and 4. Okay, cool, excellent. So let's move on so we can see where this goes. So now it says for part C, find g of 2. So I think someone was asking about this earlier. Why don't we find a value? They've now asked us to look at a specific value. And this is a little bit weird because we're going fully by a graph and not by a kind of equation or anything or function we can put it in. We're using the graph. Now this is weird because we've got to think, what happens when I put 2 in to the g function? What happens here? What comes out? So when I put 2 in as x, what comes out as y? What happens when I do g of 2 using the graph? Excellent, 0 comes out. So once I put, because I know that 2, 0 is a point, if I put 2 into this function, I get 0 out. So now I'm doing g of 0. And when I put 0 into this function, I get -6 out. So what I've basically done is when I've done g of 2, that's become g of 0, which has become -6. So it's very strange using the graph to do this, but this is something you've done before. When you've got the function, you go, okay, I plug it in, see what comes out, plug that in, see what comes out. But here we've had to use the graph fully to relate the x and y ordinates as basically the inputs and outputs. So when I put 2 in, I get 0 out. When I put 0 in, I get -6 out. And that's how you do a composite function from the graph. So the answer for this one is -6, and you've fully gone by what comes out of the graph. So very well done if you got that. Feel free to keep the comments, answers, questions coming in the chat so I know how we're doing. But really well done if you're sort of following that, because there's a lot of ideas coming together here. So excellent. Right, let's move on. Now, this is where it's a bit weird, because remember this bit was the g of x function. This was the f of x thing they told us at the start of the question. So f of g of 8, what we have to do here, again, it's a composite function. We have to see what happens when we put 8 into the g function and then use that output as the new input for the f function. Okay, so let's have a little look. Right, so we sub 8 into g of x, and when we put 8 into g of x from here, we know that the output is 4. So we're doing f of g of 8. We know that what comes out of g of 8 is 4. So then f, we're putting 4 in as the input into the f function. So I'm doing 4 going into this function here. So f of 4 is equal to 3 minus 2 times 4 over 4 minus 5, which is equal to 3 minus 8. So what's that? -5 over -1. Thanks for that comment. And I was just worried that I was going to make a really basic arithmetic mistake there. So good. I think we're good. I think that comes out as 5. Excellent. Lovely. So what we've done, this is a really useful question to be looking at, because what we've got going on here is we've got a scenario where it's given as a graph, a scenario where it's a function given as a mapping, and we're doing a composite function of using the graph and the function expressed as a mapping together to sub values in and see what comes out. So this brings together a whole load of mathematical fluency, because you're able to go from a graph with no equation, see what comes out, put it in an equation, see what comes out, and still do the composite function stuff from this really odd scenario that we've maybe not seen before. Excellent. Right, that's all good, positive feedback so far. So I think we're doing really well there. I think there's one more question we'll have a little look at now. So this one here that same function, that g of x1, so this bit is a bit redundant now, we're done with f of x. It says sketch the graph that is basically the inverse of this function here. Okay, so what we do here, what we do with the function here is basically remember that the inputs become the outputs become the inputs. So a kind of tip I would use to help get started with this is change all of these to the kind of key values on the x-axis. So we're going to have -9, we're going to have -6. Obviously, this isn't drawn very well to scale, but let's put that a little bit lower down there. And then on the other side, we've got -1, 2, and 8. So let's use that here. -1, 2, 8. Okay. And so we know that this time what was -1, -9 is now -9, -1. And it's going to be linear up to 2. And I'm going to change my axis to suit what I've just drawn. And then from there, it's going to go like that. Okay, so what I've done is I've done the inverse function of this by basically using the domain and range trick. So as I said before, remember that for an inverse function, the domain and range swap. So what were the allowable inputs of the original function, i.e. the x values, are the y values for its inverse, and the same the other way round. So basically the other thing that we haven't stressed here today that is important as well is that for inverse functions, they are basically a reflection in the line y equals x. So if you had the two graphs on the same axis, they would actually be a reflection in the line y equals x, and that's why the inputs and outputs switch. So if we were to have drawn them both on the same axis, you'd see that they're the mirror image of each other. But you'll do that with these trickier functions like e to the x and natural log of x. But hopefully we can see just swap the x and y's round is essentially the easy way. Yeah, absolutely. Good. So got through loads there. Yes, so just to backtrack on where we're at, we've gone through a load of different questions, starting off from some very basic algebraic ones, looking at the domain and range, doing the rearranging trick, finding that the domain and range swap, bit of graph sketching, graph transformations, the harder example that again was a bit of a recap from GCSE, but is still quite tough. Then this was a really useful question, I think, to have gone through because it brought together so many different ideas. So on this one, where it crosses the x and y axis have swapped as well. Okay, so where it was 0, -6 is now -6, 0, and where it was 2, 0 is now 0, 2. So that is important that you do show that as well. And so what I want to just kind of basically wrap up by talking about is if I stop sharing this briefly, and I'm going to now share quickly with you, hopefully you can see this, but do let me know if not, my other screen, is just if I could take you over quickly to the Snapify site. We've obviously got loads going on YouTube, and thanks very much for watching. I hope that was really useful. But on top of that, on the actual Snap Revise platform, which I'm hoping you guys can kind of all see over here, we have loads. We have a web classes happening all the time. We have drop-in tutors, which kind of sessions that I run to kind of go through any topics you want. So if you've got the odd question and it's nothing to do with what we've done today, that kind of service is often really handy because at A-level particularly, it's really difficult sometimes to, find an opportunity to ask a very niche specific question. And particularly with how things are at the moment, it's really good to be able to have that input and focus on some of the things you want to focus on. So the drop-in tutor stuff is a real perk for a lot of people because obviously you can ask the questions you want and get direct feedback on what you need. On top of that, we have regular web classes. So a bit like the session we've done today, and kind of loads of examples, all tailor-made for all the new courses. So a big advantage of the kind of resources available on Snap Revise is that they're geared up for the new A-level. So this A-level hasn't actually been in place very long in the grand scheme of things. And what I find a lot of my students are still doing is using websites that offer all the past papers, and they go back over it and they think, great, well, I can search by topic, I can do these old modules, but it's not geared up exactly always for the new course. Whereas on Snap Revise, it has been built completely tailored to the different boards, the different, the changes in the A-level. So as you're aware, for maths, there's loads of resources online and there's no shortage of maths questions. But what is tricky for A-level students is finding the correct resources for this new course. And I've had students before that have gone on sites, worked through a load of questions, got really stuck and said, we never learned this. And it's because the A-level has changed and bits have been removed, but bits have also been added. So on here, what we've got is we've got all the topics broken down for the spec. And we've got these diagnostic quizzes, which only take a couple of minutes. And I'm going to get a load wrong here and just guess them. But if you run through quite honestly and think, well, can I do this or not? Try these quizzes out. What we get is we get this whole scenario of basically a picture of what you know. So what we'll do is by the end of the diagnostic quiz, I'm just going to skip those of these, is we'll know exactly what questions you struggled with, what ones. I mean, it could be that you do a lucky guess and so on, but it has everything. It has the rigor, it has the notation, and really important because it will give you a picture of what you struggle with as well. And then by the end, everything's kind of grouped into what you've understood and what you've struggled with. And then the kind of stuff that's set up based on that is targeted to what you know and what you don't know. And then there's these really clear videos with lovely resources on there to help you target your revision. Because I think sometimes it's really annoying with maths videos and you have to kind of watch the whole thing and you're constantly trying to jump to the right bit, and this does it for you. And then some really nice revision guides, notes you can print out with the notation, all specific for your exam board and course. And then the exam pack, so you can do little follow-up quizzes with all nice clear solutions as well. So hopefully that's all really useful for you. And that was kind of the main thing I wanted to talk about there, is that there is a lot more to offer on Snap Revise for those that are interested. So if I stop sharing that for a second, and I'll take you back to the PowerPoint. So basically the final thing is, if you are interested in that, we have got a code for you here that expires tonight. So functions 10, appropriately named after our functions lesson today. And that will give you £10 off your first month. So it's a discount for Snap Revise, where you can make full use of all the features, all the drop-ins, directly message the tutors about questions you have, and also watch the web classes that are taking place, because obviously we're missing a fair bit of time at school at the moment, and there's a lot of contact time on there. The other thing that it does enable you to do, if you're kind of new to this, is it will let you look at previous web classes. So there's a whole backlog of lessons that you can run through and watch. And obviously in those lessons, you can, in the live ones, you can message live, just like we did today, to let me know how you're finding it. And if you have any questions kind of in real time, then that works really well. So if that's something that interests you, great. But also just a reminder that we're going to be on YouTube quite a lot still. So if you have found this useful, the maths ones at the moment are Monday and Wednesdays. So there'll be another one on Wednesday if you want to set a reminder for that. That would be great. But that was really good. I think we got through some excellent content there today. So very well done. I hope you all keep well and are able to kind of access the stuff you need for school at the moment. But as I said, we're going to be on YouTube providing these sessions quite regularly. So hopefully it'll be something that's been useful for you. well done. I hope you all take care and keep well. And I'll be doing another one of these shortly. So hopefully see you then. Cool. Right. Well done.